are essentially like recipes. Now I'm going to put this on the screen for Rachel right now. And I want you to look at the equation that's on there that says C plus O2 goes to CO2. What essentially that says, it says take one carbon, put it together with one O2, and you're going to get one CO2. Is everyone okay with that? That's a recipe. It's much like saying take one flour and two eggs. You don't take a flour, do you? Taking 1 cup of flour and 2 eggs, and you'll get flour eggs. Right? I don't know if that's a baking thing or not. I feel like it might not be.
Well, it is, but only if you take one full flour.
But if you take a look at this here, watch. Couldn't I, if I told you I had 2 carbons and 2 oxygens, couldn't you figure out how many CO2s you could make? Wouldn't you be able to figure out you make 2 CO2s? By the way, that ratio, couldn't I also say if I took 1 dozen carbons and 1 dozen oxygens, I get 1 dozen CO2s? Are you okay with that? Because it's just a ratio. Wait for it because you're going to see where I'm going. I could also say, couldn't I, for every 1 mole of carbon I take, I could react with 1 mole of oxygen and I could get 1 mole of CO2. True story? Now, let's just pretend that I'm making my own little recipe because I want to move away from the equations to write something that's kind of silly. So let's say I'm making my famous banana onion pie. Or as we like to call it, bananions. A bananion. Bananion? Yeah, bananion, right? So my recipe passed down from generation to generation is really, really simple. It's so dumb. 1 banana plus 2 onions. There's still a bunch of ends in there. I think you'll be good. And then we're going to make an arrow because we're going to make this official. Yields 1 bananion pie. We'll call it a pie. Bananion pie. Now, really quick. If I told you that I had 5 bananas, how many bananions could I make? What's the ratio between bananas and bananions?
1 to 2.
It's a 1 to 2 ratio. Now, listen carefully. As long as I have enough of the onions to react with it, would you agree with me that for every 1 banana, I get 2 bananions, right? So if I had 5 bananions, so is it a 1 to 1 or 1 to 2?
1 banana.
1 banana to 1 bananion. This is probably the worst example I've ever given. Isn't there a 1 to 1 ratio between bananas and bananions? So if I told you I start off with 5 bananas, this is terrible. I get 5 bananions as long as I had enough onions to react with it. Now, if my onions run out, do you realize I'm not forming bananions anymore? It's just truth. So let me ask you this question. Let's say I give you this. If I give you 5 bananas, so by the way, time out on this. Any guys ever cooked before or baked before? Yeah. So when you open up the recipe, it tells you the ingredients you have that you need to have for the recipe. Agree? Just having the recipe, does that mean you automatically have the ingredients? Unless it's some sort of magical recipe that produces the ingredients simultaneously while you're doing it. No, you could have a huge amount of one of the ingredients and not enough of another ingredients, and that would stop your recipe from being fulfilled. Agree? And also you need to be aware of this. If you're making a portion for like 2 people, right? A recipe for 2 people, and instead you want to make it for 4 people, couldn't you double all of the ingredients? And wouldn't that then give you double the amount of product? Why? Because the ingredients are essentially a ratio of the things you need to put together. Now, in this case right here, let's say I had 5 bananas and I have 5 onions. Now, based on this recipe, which of these 2 am I going to run out of first? Onions, right? Why?
You take 2 for everyone.
It's a 1 to 2 ratio. So put your finger on the 5 bananas. Okay, if I have 5 bananas to start with, based on the 1 to 2 ratio, how many of the onions would I need?
10.
I'd need 10, right? How many do I actually have? 5. So that means that my onions are my limiting reactant. They stop my reaction from going. And once I've used up my onions, won't I still have bananas left over? Yeah. My excess reactant. This is the first introduction to the idea of limiting and excess. Every single recipe, as soon as you run out of, are y'all with me right now? As soon as you run out of one of the ingredients in your recipe's done. Now, here's the thing. You can make something else, but the product you were starting off with trying to make, if you run out of one of the ingredients, you're done making that particular product. Agreed? Now, let's go up on the board and let's erase our banana and onion example, which I'll never use again, but you'll have this for posterity if you ever want to look at this video. Now, the easiest recipes to follow are the 1-to-1-to-1 ratios. Agree? Now, if I were to tell you in this case, I have 4 moles of carbon. Let's go 4.00 just to make it fun. Because how fun is that? And I have 6 moles of oxygen. Question is, how many moles of CO2 will be formed? So write a little question mark, moles of CO2. Now, I want you to try and do this just in your head, okay? Now, isn't everything a 1-to-1-to-1 ratio? So, freedom! Oh. So of those two, which one's going to run out first? Tell me why. I heard someone whispering very, very quietly. No, but close. We only go by the coefficients in front. That's the amount of each thing. Can you put your finger on the carbon? Up above in the equation. Doesn't that say you need 1 carbon for every 1 oxygen? Oxygen's written as O2. The coefficient in front tells me how many things of that thing I want. Are you guys with me here? I could have put in H2SO4 there, right? That wouldn't, and if I have a 1 in front of it, I just need 1 H2SO4. In this case, there's a 1 in front of that O2, so I need 1 O2. Agree? I see what you did there, by the way, Ashley, and you did as well, is you looked at the O2 and, oh, I have 2 O's. But we're not asking you what is the relationship between carbon and O. We're asking what is the relationship between carbon and O2. So that should be 6 moles O2. Yeah, if I wanted to bounce it off, how many moles of carbon do I have? Oh, it should be O2, sorry. You're right. If I have 4 moles of carbon, how many moles of oxygen would I need? 4. How many do I have? 6. So wouldn't that mean that my oxygen is my excess reactant? And as soon as my carbon runs out, doesn't my reaction stop? Let me tell you an incredibly important piece of information. Write it down in your notes. Oh, by the way, if you look in the notes that I gave you, the note packet that we've been using up to this point, you can flip forward, and it's going to come to a section of like using balanced equations, and it starts talking about limiting reactant. You guys have the note packet. Yep. At the very bottom it says limiting reactant. Sometimes, by the way, instead of saying limiting reactant, we'll say limiting reagent. They're kind of the same thing. Here's the important statement of importance, as I'm being redundant. You must always start with the limiting reactant when you want to figure out an amount of product. You must always start with the limiting reactant when you want to figure out amount of product. You have your name and section number on it? Thank you very much. Okay, what does that mean? Well, humor me for just a second. If I tell you I have 4 moles of carbon and I ignore the oxygen, right? In theory, if I start with 4 moles of carbon, how many moles of CO2 would I be able to form if oxygen was not a question, if I had an infinite amount of oxygen? Wouldn't I be able to four moles of CO2? Are you guys all with me? Now, let's pretend I have 6 moles of oxygen, which I do, right? And let's say I'm ignoring my carbon, right? Let's say I have an infinite amount of carbon. How many moles of CO2 could I form from 6 moles of oxygen? Wouldn't it be 6 moles of carbon dioxide? Do you see that if I start off with my limiting reactant, the one that gets used up, I can only form 4 moles of product. If I start out with my excess, the excess is going to tell me I can form 6 moles. Well, that's a lie, right? Because as soon as I run out of one reactant, my reaction stops. Do you understand this here? The best example I can give you with limiting reactant is like getting on a plane. Let's choose United. So let's pretend that you're getting on a United flight, and rumor has it they overbooked their flights, every single one of them, right? And you happen to be one of those people that gets on the plane, but then realizes you're bumped because someone with higher priority is going to take your place. You know why that happens and why they don't just say, come on in. You know why they do that? Because the seats are the limiting factor in who gets to the destination. If the plane has 250 seats on it, guess how many people maximum are going to get on that plane? 250. If there's 300 people waiting to get on that plane and really want to get to that destination, it doesn't matter because the plane itself can only accommodate 250 of those people. Are you guys with me on this? So whenever we have a reaction and you have 2 reactants, one of them will run out first. That's your limiting factor, and you need to use that amount to figure out how much product you're going to get. Now, before we get too into limiting reactant, I'm going to give you a couple of problems to work with where we assume I tell you right up, this is the limiting reactant. Now, there's 2 ways I can tell you have a limiting reactant. One is this. Ready? Carbon is reacted with excess oxygen. Now, looking at that equation, if I say carbon is reacting kind of in the middle of the screen there. Yeah. If I say carbon's reacting with excess oxygen, doesn't that mean that oxygen, I have an excess of it? It's silly that way, right? And doesn't that mean that carbon, therefore, is my limiting reactant? True story? That means that I can use the limiting reactant to solve the rest of my problem. Now, let's do this together. Can you erase that? And let's change the equation. And let's go N2, same size, N2 plus H2 goes to NH3. Now, one of the really, really important things that we've covered before is you got to have a balanced equation, agree? Never more important than now is having a balanced equation, because if you have, look at it like the way it's written right now, doesn't it appear that you need 1 N2 for every 1 H2 to get 1 NH3? But in reality, as she's jumping ahead to do wonderfully, it's a 1 to 2 to 3 ratio, right? Or 1 to 3 to 2 ratio. So now watch what I can do here. Let's do a problem. Right at the very top, as high up as you can write, you say if 7.69 moles of hydrogen reacts with excess nitrogen, how many moles of ammonia are produced? Now, a couple of things you need to be aware of here. We have 2 reactants, right? Haven't I told you which one's the limiting reactant now? Whichever one's not the excess reactant. So in this case, which one is the limiting? Hydrogen, H2. Agree? Secondly, I'm asking you how much ammonia is going to be produced. Now, some of you are like, teacher, what is ammonia? Well, let's play the game called, what's the only thing being produced? NH3, right? If I tell you that I'm producing ammonia and there's only one thing being produced, click, 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 ammonia is being produced. Does that kind of make sense? Now, how do we figure that out? Well, let's start by writing the moles that we're given in the problem in the upper left-hand corner of our table of death. Now, the table of death that we've done is actually an incredibly, incredibly helpful thing. Are you with me? Because we don't have to memorize multiplying and dividing from here on out. We can just follow the table to get to where we want to go. So let's do it underneath it so we have a little more room because we may go a little bit farther. So let's go 7 point, what is it? What did I give you? 7.69 moles of N2 in the upper left-hand corner. Incredibly important from here on out. Those of you are like, I hate units. They're my least favorite. You with me? You must put them in here because not only are we canceling out units, but we're actually changing from one unit to the next. So let me ask this question. We want to go from moles of N2 to what? Moles of NH3. Can you put like a swoopy arrow from N2 in the actual equation? From N2 over to NH3? The only way you can ever move from one thing to another in an equation, the only way is by using the coefficients in front and their mole ratios. So help me out here. What is the ratio between, and are we using N2 or H2 to start off with here? Did I give you grams of N2 or grams of H, or moles of N2 or moles of H2?
H2.
So you better start with moles of H2 in our equation, right? I'm sorry, I couldn't really see what you wrote there. Did you write 7.69?
Yeah, sorry, I wrote the wrong thing.
So 7.69 moles of N2 is what they give, or H2 is what they give us, right? So help me out here. What's the ratio? Let me backtrack. Can I make this statement? Because I should have made this statement before. Do you realize that all of our equations, every chemical reaction you write is written in moles? Do you understand this? So if I read that equation, put your finger on the N2. It says 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. All of our equations are written in moles. So I know right now the ratio of all of the moles to each other. Now, are we trying to get from H2 to NH3? And isn't the ratio for every 3 moles of H2, I get 2 moles of NH3? So I'm starting at moles of H2 in my table, right? So couldn't I use that conversion factor between the two of them to go from moles of H2 to moles of NH3? On the bottom, can you write 3 moles of H2? On top, can you write 2 moles of NH3? Did anyone see what I just did there? It's like saying, for every 3 bananas, I need 2 apples. Right? If I tell you the number of bananas, can you figure out the number of apples by using a 3-to-2 ratio? The coefficients give us that ratio. Now in this problem, didn't they ask us just to solve for moles of NH3? So we can cancel out the moles of H2 on the bottom and make an equal sign on the end. And wouldn't we take the 7.629 and multiply it by what? And divide it by? Someone do that, please. Five point 1.2. You write moles of NH3. All right. Pretty straightforward problem, right? Let's take it one step farther. Can you erase the bottom part? Yep. And this time, instead of saying moles of H2, let's say given 6.93 grams of H2. How many moles of NH3? Can you just change the number up above from that moles to grams? That's the problem now. So tell me what the problem is that we have right now. Yeah, so watch. if my recipe calls for moles and I give you grams, I cannot use moles as my recipe. It's kind of like this. I don't know what unit you do in baking, but isn't the cup a unit of measurement? So if I need to have a certain number of cups of something, because my recipe is written in cups, and all I have is a teaspoon, right? Mustn't I know the conversion between teaspoons and cups to be able to use the equation or use the recipe? In this case, all of our recipes, all of our equations are in moles. Now, to lesser students, this would be troublesome, right? But don't we have an easy way of getting between moles, grams and moles? Which you just did, right? Can you do me a favor?
Yeah.
Stop right now, because we're going to do multiple steps.
Okay.
So erase the equals H. Would you acknowledge right now, can you write 1 mole of H? It's H2, by the way, not H.
Okay.
H2, H2, and can you write 1 mole of H2 on the top? So watch, and I want this to be incredibly straightforward. For those of you struggling here, hang in there, man. Class stops very shortly. Actually, okay, still 20 minutes, but close, right? Thank you. All right, watch. If they give 6.73 grams of H2 and they ask us how many moles of NH3, realize the only way we can go directly from H2 to NH3 is if we know that N2 is excess, right? Yeah. If it wasn't excess, we'd have to actually figure out which one was the limiting reactant, because we can never solve a problem without starting the limiting reactant. But now watch. If I go from grams to moles, aren't I now able to use the mole ratio between H2 and NH3? So we're just doing one step farther than we did before. So can you put the 3 moles of H2 on the bottom and the 2 moles of NH3 on the top? Cancel out the moles of grams, moles, moles. Can you underline the moles of NH3 or circle that moles of NH3 in the problem right there? Yeah. Yeah. Yeah, and we only really wanted the unit, but that's still fine. Okay, now watch. Right now, if I did the math, wouldn't I know how many moles of NH3 I could produce? But what if I'm feeling greedy? What if I want you to tell me the grams of NH3? So let's pretend the problem right now says, it says how many moles of above. I'm changing the problem on the fly because we can do that, and it's not going to make your problem any different. Let's make that 2 grams of NH3. So watch, couldn't we just go one step farther? And could we go 1 mole of NH3 on the bottom? And then the molar mass, I believe, is going to be something like 17.03 or something. Yeah.
Wait, how'd you figure out the gram? Just ask.
All the molar masses from the periodic table of NH3. And one of the things that she's done a really good job of is keeping what the reactants and products actually are in each case. So moles of NH3 cancel out. Aren't we at grams? So then all that's left isn't just to multiply everything on the top and divide by everything on the bottom. Now let me share with you a really important trick. One of the things you have to be aware of is this, is that, ever listen? You can put in your calculator the 3 things on the top in parentheses divided by the thing all multiplied by each other, divided by in parentheses the thing on the bottom all multiplied by each other. But what you can't do is this. You put your finger on the 6 point, as I say the numbers, just write them out. You can't do this. 6.73 times 2 times 17.03 divided by 1.008 times 3, because that times 3 means you move it to the top. Do you follow? So here's the easiest way, and you never have to use parentheses. Watch. This is what you're going to do. Start at the very top again. 6.23 times 2 times 17.03 divided by 1.08 divided by 3. So what you can do is hit multiply over and over again until you've done all the things on the top, and then hit divided by over and over again on the bottom until you hit all of the things, and hit equals, and that gives you the answer. That's the easiest way to do these problems.
Did anyone else do it? Or am I just on the line?
And I think that's the problem with being uber diligent, that other people just then rely on you to do stuff. Can anyone verify that?
Yeah, I'm doing that.
Do you have units on the end of that?
I got 78.
Yeah, I got that.
By the way, isn't the only thing I'm adding in right now the mole ratio between two things that we're having to solve for? Okay, let me give you another problem using the same exact equation, see whether you can solve it. Erase, and let's change the value up on the top. We're going to change it a little bit differently.
Same equation.
Same exact equation. Let's erase the question, and I want to see if you guys can problem solve this on your own. Okay, if I'm going to change everything. Yeah. If 97.00 grams of NH3 are produced, how many grams of N2 must I have started with? Now,
H2 is still excess.
no. So watch. Everyone listen. Haven't I told you how much product I have?
Yeah.
So if I know the amount of product that I already got, I can know exactly how much reactant of each kind I must have used. So we don't have to tell which is the excess, which isn't, because I could ask for either of those two reactants. If I actually formed a certain amount of product, that means that I must have used a certain amount of each of those reactants. Now, one of them might be in excess, right? But the amount that I used of it is going to be able to be figured out even if I have more than I needed to. So in this problem right here, what am I starting with? Can I encourage you guys, every single time you do a problem, if you're like wondering, where do I go from this? And incidentally, those ratios, they allow me to go backwards and forwards in a problem. Because in this case, we're going from NH3 to where? To N2, grams of N2. Can you put a little arrow from the NH3, like the soupy arrow from the NH3 towards the N2? Yeah? Now, here's the thing. Don't I know, if I can figure out the moles of NH3, don't I know that for every 2 moles of NH3, I get 1 mole of N2? But I got to get to moles. Did they give me moles to start with? So can I encourage you with this step? If they ever give you grams, your first step has to be to convert to moles. Has to be. Wait for it. What if I gave you atoms? Couldn't I do that as well? Well, this equation is not written in atoms. Isn't it written in moles? So can I convert from atoms to moles if I had to? But let's just start with these ones right here. So we're at grams of NH3. Does everyone see the first step has to be getting to moles? Let's do it. I would love for you guys to be trying this as you're doing this alone.
For atoms, doesn't matter. It's the same ratio.
6.02 times 10 to the 23rd.
But it's all same ratio.
You're right. Good catch. But you're going to have to apply the ratio. So if it's a 1-to-1, yeah. But if it's a 1-to-3, you're going to have to multiply your number of atoms you have by 3. Right? Good catch, though. Really quickly. Rachel, will you tell everyone what you've just done?
Okay, so I just found the molar mass of NH3, which is to add up the molar mass of each one, and then you had to be NH3 to cancel it out. I converted to one mole or 97.
Well, if we multiply it out, we
Yeah.
know what the moles are. But right now, if we did the math, wouldn't we know how many moles of NH3 we're starting off with? But we want to go from moles of NH3 to what? To grams ultimately of N2. But listen carefully on this. The only way we can move between things in an equation is by using the mole ratio. So I have to figure out the moles of one of the things, which I just did, NH3, and then couldn't I use the ratio to figure out the moles of the other thing? So we're going to have to put in that equation the ratio. Isn't the ratio 2-to-1? Everyone in the classroom, are you with me on this? So in this case right here, where am I going to put, and how, explain why you're putting things where you are.
So I'm trying to cancel out because I want to get just the 1 mole of N2. So I have to put it on the bottom to cancel these out. So now these will cancel. And then since it's a 2-to-1, since there's two
ammoniums, yeah.
and or 2 moles of nitrogen here, and there's only 1 here. This is going to be 1 mole and 2.
Mhm.
And from there we can work.
Yeah. So now I want you to pause here because at any point in the way, if Rachel's like, you know what, I've grown weary of this problem, I want to solve. If she were to stop right now, she would know how many moles of N2 there were and that many grams of ammonia. But the problem didn't ask for moles, didn't ask for grams. So we're going to go one step farther and we're going to convert to grams. Hang in there, Jenny.
Do I do like 14.0062 times 2 or just?
Yeah. So when we're using the molar mass, we have to get the molar masses of all the atoms that are involved in the compound. Okay. Can you write grams of H2 on there? Sorry, N2. That was my best speak. So you guys see how we just followed the steps and ended up with the unit that we wanted. And then it's a matter of this. Don't we have multiple things on the top and multiple things on the bottom? So on your calculator, literally all you're going to do is punch in all the things on the top, multiplied by each other, and then divide by everything on the bottom. So literally you're going to go multiply, 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 divided by, or in this case, multiply, multiply, divide, because there's only 2 things on the, or are there 3 things on the bottom? There's just 2 things on the bottom, 2 things on the top. What number are you going to get? Go ahead. Oh, by the way, even when we're doing these types of problems, do you realize that significant figures are alive and well? So how many significant figures should we probably have in our problem?
4.
I gave you 4 to start with, right? And I'm assuming that throughout the problem, and I think you did a good job with this, you wrote with the significant figures for the molar masses, you always did more than 4 significant, or at least 4 significant figures. So that's not going to limit us. But let's say you're like, you're in a mood, and you're like, I'm only going to use 3 significant figures for my molar masses. Well, then your answer has to have 3 significant figures. Any questions on what we're doing right now? So, yes, no? Okay, so watch. Before we get into like solving for limiting reactants and such, I want to just have you guys get used to going back and forth between problems. You guys had 2 worksheets, right? One of them, I believe, said limiting reactant worksheet 1. Can you show it for me real quick?
We have limiting
so?
reactant and excess reaction worksheet, and then limiting reaction worksheet 1.
Okay, I want you to do the one that says limiting reactant worksheet 1. Now, I want you to, does everyone have it in front of them? This way you can show the worksheet to the people on the screen. Okay, in all of these problems, they let you know which is the limiting reactant when you need to. Now, does everyone understand if I start with an amount of product, I must have used a specific amount of reactant, so I don't need to know what the reactant amount, I don't need to know which is the limiting reactant. But if I start you with reactants, you always have to start with the limiting reactant. So look at how it's written in problem A. Ready? It says how many moles of ammonia are formed if 6.3 grams of hydrogen gas reacts with what? Excess nitrogen gas. What does that mean about my hydrogen gas? The limiting reactant, which is why I can go directly from hydrogen gas to ammonia. Are you with me? Let's look at the next problem. If you produce 312 grams of ammonia in a perfect world, nothing is lost in the environment. How many grams of nitrogen gas must you have reacted with excess hydrogen? So aren't we just going, in this case, from grams of ammonia to grams of nitrogen? Now, look at A and B on number 2. And here's the problem that you're going to face moving forward. See how it says potassium chlorate decomposes in a reaction, and I don't give you the actual reaction? Guys, remember like last unit when we did, or 2 units ago when we did predicting reactions? Metal chlorates always form a metal chloride plus oxygen. Now, I'm going to help you with this here just because I don't want you to focus on the reactants, but I want you to see that this is how questions are going to be given to you. So why don't you guys write this down? Can you grab another one of these here? I will tell you what the formulas are. I will not balance them for you or anything, but this will help you in doing these problems, yeah? So potassium chlorate, this is the general equation. KClO3, you should be writing this down. KClO3 yields KCl plus O2. That is not balanced. Number 3, Mg plus O2 yields MgO. Again, not balanced. And then the last one, I actually gave you the equation. So I want you to partner up in the remainder of class. This is the only worksheet that's homework. This next worksheet is what we're going to be doing next class, the limiting reactant and excess reactant worksheet. So thank you so much, Rachel. You were wonderful up there. Homework is limiting reactant worksheet 1. I'm going to put that onto the portal right now.